Hey everyone, and welcome to this explainer. Have you ever stepped outside on a perfectly clear night, looked up, and just stared at the moon? It's this massive, glowing rock just seemingly suspended out there in the dark void of space. It's a beautiful, almost cinematic mystery right above our heads. But when you really stop to think about the physical reality of a giant sphere hanging up there, it brings up a fascinating puzzle, one that completely reshapes how we view the cosmos. So today, we're going to totally change how you look at gravity.
Okay, so here's the ultimate counterintuitive hook. Think about it for a second. Earth's gravity is absolutely relentless. It pulls everything down. I mean, if you toss your keys or a baseball into the air, it inevitably comes right back down to the ground. Gravity literally never takes a day off. So why does this incredibly massive object, the moon, just stay up there? Is it magically escaping Earth's gravitational grip? Does it have some sort of invisible force field?
Well, the truth is going to absolutely shatter that preconceived notion. The moon isn't just peacefully floating or hovering in space, it is actually plunging toward Earth every single second. Yeah, you heard that right. The moon is in a state of eternal, constant free fall toward our planet. But if it's falling, why hasn't it hit us yet? That right there is the key to this entire mystery. And to figure it out, we've got to go back in time a bit.
Section 1. Newton's Mountaintop Experiment. Scaling the cosmos down to a simple throw.
To make sense of this crazy paradox, let's look at a really brilliant thought experiment from Isaac Newton about projectile motion. He basically scaled the massive mechanics of the entire cosmos down to a simple, everyday human action. Picture this. You're standing on the peak of a tremendously high mountain, way above the atmosphere. Now, step 1, you throw a ball forward. It travels a bit, curves down, and hits the ground. Standard stuff. Step 2, you throw it a lot harder. It goes much further before gravity eventually pulls it down. Now for step 3, imagine there is literally zero air resistance to slow the ball down, and you throw it with immense speed. The ball is still falling, for sure, but because the Earth is a sphere, the ground is actually curving away from the ball at the exact same rate the ball is dropping. The curve motion flawlessly matches the Earth's curvature, creating a perfectly stable orbit. So the ball is falling forever, but the ground simply isn't there to catch it.
Section 2. Gravity versus forward speed, the ultimate cosmic balance.
To really grasp this cosmic tug-of-war, we have to realize the moon is doing two things at exactly the same time. First off, Earth's gravity is aggressively pulling it down, trying to drag it straight into the surface. But second, the moon has an unbelievable amount of forward speed. It is rocketing through space at roughly 3,680 kilometers per hour. It's this exact, precise forward speed, constantly battling Earth's downward gravity, that creates the smooth circular motion we see when we look up from Earth.
Now the really crucial point here is understanding what would happen if we messed with this delicate balance. Imagine a cinematic, totally catastrophic scenario where some magical force instantly stops the moon right in its tracks. Its forward speed drops from 3,680 kilometers per hour to absolute zero. What happens? Well, without that forward momentum, the moon completely loses its power to advance. Earth's gravity would immediately take full control, pulling the moon straight down, leading to a direct and catastrophic crash into Earth. Thankfully, physics ensures that is not happening anytime soon.
But hey, let's flip the scenario for a second. What if the moon kept all its forward speed, but Earth's gravity just vanished, suddenly disappeared? Well, without that constant downward pull, keeping it tethered in its curved path, the moon would immediately stop orbiting. It would just obey its own momentum and shoot straight off into the dark, infinite expanse of deep space in a perfectly straight line. So that downward pull, it's absolutely essential.
Section 3. Satellites and modern aerospace. How falling keeps us connected.
You know, this brilliantly illustrates a concept that goes way beyond just natural moons and planets. Let's pivot from the moon to human-made objects, because modern aerospace engineering literally relies on this exact same principle. Every time you check the weather on your phone, use your GPS, or watch a live feed from the International Space Station, you are relying on the physics of falling. The ISS, modern communication satellites, weather monitors, none of them are truly floating. They are all constantly falling toward Earth. Our engineers connect these exact principles to the practical engineering required for satellite deployment. They launch these critical technologies with enough lateral speed so that as gravity pulls them down, the Earth curves away. These orbital mechanics ensure our communication satellites remain perfectly stable. They are just missing the ground over and over again, allowing us to stay globally connected. Section 4. Earth's Tides and Future. the long-term consequences of an evolving orbit.
All right, let's zoom back out to the cosmic scale for a minute, because this perfect orbital dance, it isn't actually entirely static. Brace yourselves for a really surprising fact here. The moon isn't staying at the exact same distance. Every single year, it drifts away from Earth by approximately 3.8 centimeters. That is roughly the length of your fingernail. This incredibly slow but steady retreat is caused by tidal forces, basically the gravitational friction between Earth's oceans and the moon. And because of this, over millions and billions of years, the moon will be noticeably further away than it is today.
So why does a few centimeters a year actually matter? Well, the moon basically acts as Earth's gravitational anchor. With the moon, we have stable marine tides, a stabilized rotational axis, and a balanced, livable climate. All of which, by the way, made complex life on Earth possible. Without it, or as it moves drastically further away in the very, very distant future, the consequences are intense. We could face unpredictable waters with significantly altered tides, a wild planetary tilt, and extreme, totally chaotic weather. The moon isn't just some pretty nightlight. It is a vital, absolute stabilizer for our world.
To pull all of this together into one clear foundational lesson, especially for anyone studying basic physics out there, it really all comes down to this one quote. The moon doesn't fall to Earth because it is moving forward so fast that it misses the ground. That is the absolute essence of what an orbit is. It's simply the art of missing the ground while constantly falling.
Section 5. Test your orbital knowledge. Let's review the mechanics.
Okay, you guys have been fantastic so far, but now we're going to put your focus to the test with a quick rapid-fire review. Here is question number 1. Think back to our cosmic tug-of-war. What are the two distinct forces that must balance perfectly to create an orbit? Got it in your head? It's Earth's downward gravitational pull fighting against the object's tremendous forward speed.
All right, question number 2. Let's see how good your memory for metrics is. At what exact forward speed is the moon traveling to ensure it continuously avoids hitting the Earth? Did you remember it? The answer is roughly 3,680 kilometers per hour. That highly precise velocity is literally what keeps us safe from a catastrophic collision.
And finally, question number 3, going all the way back to Newton's original insight. If you threw a ball off a mountain with absolutely zero air resistance, what dictates whether it just falls to the ground or achieves orbit? It's the forward speed. If you throw it fast enough, the curvature of the falling ball exactly matches the curvature of the Earth right beneath it.
Well done! You've officially mastered the mechanics of our local cosmic neighborhood. But as we wrap up this explainer, I want to leave you with one final, kind of provocative thought. If perfectly balanced orbits govern literally everything from our communication satellites to the moon, what other massive ancient structures out there in the vastness of the universe are secretly just falling, locked in their own eternal descent? Next time you look up at the night sky, remember, nothing is truly floating. Everything is falling, moving just fast enough to miss the ground. Keep looking up, keep asking questions, and I'll catch you in the next explainer.